Let's start with some definitions. So a dilation is a transformation that produces an image that is the same as the original, but it is a different size. All right? A dilation is similar. So in math, similar means that it has the same angle measures. It also means the ratio of side lengths are proportional. So what those two things mean is, an easy way to kind of put it out there is, you know how like on a cell phone or tablet, if there's like a little picture on there and you zoom in, it's the same exact picture, just bigger on your screen. All the things are in proportions. All the angles are the same. Okay? That's a dilation. Also, if you take something big and you make it smaller, and it keeps all the same ratios and the same angles, it's the same thing, just smaller, that's a dilation. Now, when you start distorting a different direction, that gets a little different. So if they're similar, it means those two things, same angle measures, and corresponding sides form proportions. Dilations, for our purposes, are going to be centered around the origin 0, 0. That's why I deleted the Khan Academy dilations of triangles. That started centering you around a point that wasn't the origin. So we're going to just focus on origin only. You guys have done scale factor last year. Scale factor is a ratio of the image to the pre-image. So remember, the image is the new, the pre-image is the old. And for a lot of scale stuff, I like the ratio myself, fake to real. So like when you're doing blueprints, the fake is the blueprint, the real is the actual house. When you're doing a cellular model, the fake is the bigger model, the real is the actual cell. That helps me keep the right things. So if I was using the fake to real for scale factor, the fake would be the new one and the real would be the original one or the pre-image. So I like the fake to real ratio. That just helps me keep things straight with all scale factor, whether it's a 3D model, whether it's a drawing, everything. So I use the fake to real like in my head, but really what that is the image or the new to the pre-image, the old. And that's going to be important. You want the right scale factor, otherwise it's going to be getting big when it's supposed to be getting small when it's supposed to be big, if you mix your ratio up, right? So we all have to use the same ratio for scale factor. If it's greater than 1, what happens when you multiply by something greater than 1?
It gets bigger.
It gets larger. You might see the word enlarge. Okay? Between 0 and 1, what happens to your number?
Smaller.
Smaller.
And small.
Reduced. You might see that. Okay. And so right here, what operation is happening when we do a dilation? What operation is that? When we write things next to each other, no symbol. Yeah, Lucan.
Multiplication.
Yeah, we're going to multiply. Or divide, which multiplication is division, right? When I multiply by 1/3, I'm dividing by 3. Okay, so scale factor of 3, how would I write the rule? So I'm doing my arrow rule. I got x, y. A scale factor of 3, it's going to be 3 times the x value and 3 times the y value. Less thinking. I think rotations are the hardest. I don't know about you guys. The most thinking for a rotation. All right, guys. Let's look at this example 2 on your notes. So you got this triangle. You got some vertices. And we got to use a scale factor of 4. So let's get organized. I know it's written right there. You know me. If I can be more organized, I'm going to be more organized. And then I'm going to write my rule. So scale factor of 4, what am I multiplying by? 4. So for A prime times 4, I get 0.8. For B prime times 4, I get 16.16. And for C prime times 4, I get -4.16. I know I wrote fast, but you're going to be able to catch up. I just multiplied everything by 4 to get a scale factor of 4, right? Yeah, it's cool. Less thinking, which thinking's good. Don't poo-poo when I'm thinking, but less thinking than rotations. Rotations hurt the brain a little more, I think.
Yeah.
All right, guys, let's make this quadrilateral. Our pre-image, we have -2, 4, 4, 4, 4, negative 2, and negative 4, negative 4. Anybody know what this shape's called? It's a special quadrilateral.
Square.
Nope.
Oh.
It's called a kite. It actually looks like a kite, which is kind of cool. Kites have congruent sides. These sides are congruent.
Oh, kind of looks like.
Well, it's called a kite. I'm using your notes here, huh? You feel free to write on them, though. Okay, so we need to do a dilation of a scale factor of 1/2. So for our rule, xy is going to become 1/2 x, 1/2 y. I'm just writing a different way. I felt like writing it like this. You could also write it like, it's the same thing. Ultimately, I'm dividing by 2, right? So for p prime, I'm going to divide both my values by 2. I get negative 1, 2. For q prime, I'm looking up here for my points, guys. Are you looking up there still? For q prime, divide both by 2, I get 2, 2. R prime, divide both by 2, I get 2, negative 1. And S prime, I divide both by 2, I get negative 2, negative 2. So I'm going to plot my points. I should have labeled my original points. It's q prime, that's q. 2, negative 1, that's r prime, that's r. And negative 2, negative 2, that's s prime, that's s. And I think these images are kind of fun because if you were to make a bunch of them, like if you just did like 0.8, 0.8, 0.8, 0.8, it'd be the same picture just inside of itself. It'd be really fun, I think. All right. So we have not figured out how to find distance on a coordinate plane yet. On this one, I'm going to show you that we can just count. All right. So we're only going to demonstrate that our sides are similar and they form proportions. Here's what we're going to do. We're going to find the length of PQ and the length of P prime Q prime. And then we're going to find the length of QR and the length of Q prime R prime. And the reason I want to pick those is because we can just count those. So PQ has a length of 1, 2, 3, 4, 5, 6. P prime Q prime is 1, 2, 3. QR is 1, 2, 3, 4, 5, 6. And Q prime R prime is 1, 2, 3. Okay, so if we're doing fake to real or image to pre-image, we have a ratio of 3 to 6 for both of those, right? So our sides form that scale factor proportion of 1/2. You seeing that? 1/2 and 1/2? Cool. So that's proving that our sides form proportions. Again, we could do the other ones. We're going to have to do it on a later one. I'll show you how to do that when we get there. But this one, we could just count some sides. I just counted, and I made the ratio of the scale factor being 1/2. So my sides are proportional, right? 3 to 6 is the same thing as 3 to 6, right? 18 equals 18, 1/2 equals 1/2. Cool. What is also true about the angle measures? Yeah, angles are congruent. You're going to write that at the bottom of your page. But the angle measures are all the same. Whether you had a teeny quadrilateral or a huge one, they keep their same angle measures. All right, guys, this one should be pretty quick. Let's write the rule for a scale factor of 5/2. So xy, what operation do I use for scale factor, guys? Multiplication. So there's my rule. Is it going to get larger or smaller, James?
Oh, it's gonna get larger, but can I say 2.5?
You could, but it's way easier to multiply by these fractions because you'll be able to cross simplify. Fractions are our friends. Okay? All right, guys, so let's get organized. So A, B, C, D. My points are 6, 0, 0, 6, negative 6, 0, and negative 2, 0. And I've got A prime, B prime, C prime, D prime. And I get 2, 0, 0, 2, negative 2, 0, and 0, negative 6. So what happened to all my points?
1/3.
From x, y, it went to, everything's a third, right?
Yes.
So 1/3 x, 1/3 y. But I'm going to show you something really cool about these angle measures. You ready for this? This is next level stuff, guys. So I'm going to find how long that is and how long that is, and what should the ratio be?
1/3.
1 to 3. But the diagonal is longer than like when we're looking at one box, right? The diagonal is longer, so I can't just count diagonals. How could I find the diagonal? I can make a triangle. So watch what I'm gonna draw in here.
Ooh.
The blue line and the blue line. You seeing that? Now I have what type of triangles?
All right.
Right triangle.
And you can measure the side.
And I got a 6 and a 6. I got a 2 and a 2. So watch this. Check this. For the big triangle, I know that 6 squared plus 6 squared equals my hypotenuse squared. Now, to make this a little simpler in my calculator, check out what I'm going to do here. How do I get rid of the square on the C?
Square root is.
So that means C, or the hypotenuse, can be the square root of 6 squared plus 6 squared.
Yes. Can I see it?
So that's the square root of 72. And we're just going to keep it like that. Because it's going to be irrational, right? So let's go to the little triangle. We'll do the little triangle down here. I know that 2 squared plus 2 squared is C squared. And I can get rid of the square on the C like this. So that's going to be the square root of 8. Follow? This is actually the distance formula. We'll do the distance formula later.
Easy.
The Pythagorean theorem is the distance formula. I just need to make the connection for you later. So, to get the ratio of fake to real, or pre-image to image, that is square root of 8 over square root of 72. And if you do that in your calculator, you get 1 to 3. Okay? Square root of 8 to square root of 72 is 1 to 3.
Yeah.
It's pretty cool. But did you see how we found a diagonal distance on there by just using the Pythagorean theorem? It's pretty cool. Just like the dog trying to get the stick through the door.
Yeah.
Thanks, Susie. That's 0. No, I got it at the wrong spot there, too. That one's... D is 0, negative 2. Man, I had all kinds of points wrong there, Susie. Oh, that 0. That was right. 0. It's over here. 0, negative 2.
You gotta remember.
There we go. Thank you, Susie.
Remember the Alamo.
Here we go. So we've got x, y, z. Negative 1, negative 1. Negative 1, 2. And 1, 1. Man, I keep writing things that I'm not saying. All right. Dilation scale factor of 2. So writing my rule, what's going to happen to x, y? 2x, 2y. So x prime, y prime, z prime. So everything's times 2. Cool, cool. Let's go with this color. So I'm going to draw my new image. Negative 2, negative 2. That's x prime. Negative 2, 4. Y prime. And 2, 2. Z prime. I'm going to draw the straightest lines I can. All right. Now, guys, why, on all the other ones, it looked like the picture was inside the picture, kind of. Why is this one not inside the picture? Looking.
Because it's right on the origin is on the side of one of the
Yeah.
in the middle of one of the sides.
Yeah, so we're dilating around the origin, which means we're going to if a point's right there, that point's getting multiplied by 0, 0. So your dilation, if it gets multiplied by 0, what's going to happen? 0.
Yeah.
So it doesn't matter what we dilate that figure by, it's always going to pass through the origin, unless we dilate by a different point other than the origin. So y prime after a reflection, let's write that rule. After the reflection, what's going to happen to y prime? Across the x. So across the x, I like doing this motion, up and down. So what's changing across the x? The x or the y? y.
The y, yes.
Ooh, my arm was getting tired there, guys. So it's going to become x negative y. So y prime is currently negative 2, 4. If I reflect across the x, it's going to have to be
Negative 2, negative 4.
negative 2, negative 4. The y's got to become its opposite.
Hey, I did that.
And so you can also look, if you folded your paper along your x-axis here,
Symmetry.
that would line up with the y double prime. Alrighty, tighties, get after it.
Oh, I did the